Esa sí, hay un candidato o candidata. Yo estuve pensando un poquito.
Ladies and gentlemen, it's welcome to it's a pleasure to welcome those of you who are new to Nordida. So many of you have maybe heard about Nordida in the past, at least when it was back in Copenhagen. Nordida moved to Stockholm about 3 years ago, and for various reasons, after having had a successful life for 49 years in Denmark. So one of the reasons of Nordida's existence is, of course, to be useful to the other Nordic countries. That certainly used to be one of the main objectives of Nordida. And the vision has changed a little bit over the decades because the times have changed significantly. Back in those days, things like postdoc positions hardly existed as they do exist now. So that was one of the reasons why the mission has to adapt to the new situation. One of the new developments in many countries around the world is the development of program activity. And so that's something where Nordida is now also playing a part in this. And this is here one of the mini programs. There used to be and is a schedule around the year full with various programs of a length between 1 and 2 months. And that is an idea to make contact between Nordida and the other Nordic countries and certainly the rest of the world. Otherwise, Nordida is still having a number of postdoctoral positions, and it's having assistant professor positions, giving more advanced people an opportunity to really develop their research careers in ways that is not so easily possible at research institutions where people have much more teaching duties already at these somewhat more advanced postdoctoral ages. So here, on the other hand, people get sufficient support so that they can run meetings and programs which allows them to become prominent in the rest of the world. So with these words about Nordida, my name is Axel Bonnenburg. I didn't say this. I'm one of the permanent staff here at Nordida in astrophysics. The director at Nordida is Larus Palacios from Iceland. He is not here today, but he will be here tomorrow again. And our deputy director is Ulf Bargrim. And he just left 15 minutes ago for some other political reasons. Meetings and stuff. So I think that's all I need to say. If there are any things, any aspects regarding this program that are where you would like to have some help, please feel free to contact me. I'm normally sitting in the other building, in the other Nordida building, which has the street address. This, by the way, for those of you, this noise here, is not a thunder. It's actually the roadwork beneath the ground here. And this is quite serious business, and it's hopefully very useful for the future traffic, because it will significantly alleviate the traffic load here in the Roslagsstulz area. So, but if there's anything about any organizational issues, please feel free to contact me, or otherwise, of course, the directors or the program organizers. So with this, let me then welcome Niels and Lars, and wish them full success for this new program.
Thanks. So we felt that we should have at least one actual member of Nordida give some welcome, given that Lars and I are not local. I'm certainly not local at all, and Lars used to be. We're all scroungers, really, on Nordida money, so thanks for that. So this program on neutron stars, the crust and beyond, will run for 2 weeks. We've got quite a lot of people here already. There will be people arriving and departing during these 2 weeks, so some people are here now. The program is very light on talks, because the main purpose is to get people talking. We feel that we do that best by leaving lots of space and just letting them sit around and get bored until they have to spring into action. Or rather, so the talks that we will have, apart from this introductory talk that will come to soon, will essentially be aimed at focusing on the key issues as we see them, and explaining what the problems are, and what the key issues are that we'd like to make progress on, and probably just explaining why we're ignorant. And those will be essentially 10 o'clock every day, followed by, in some cases, some shorter contributions that focus on one particular issue, a discussion point, if you like. And we would very much welcome people, other participants in the program now, to volunteer additional pieces if they like, or just prepare them for the day. You know, spring into, jump into the discussion as you like. The key points, as I said, is to talk to each other and get things done. Okay, so that's the program. So there is a program. It is available on the web, on the website. So you can. It will, I suspect, develop a little bit as we go along. The long presentations at 10 o'clock will not change. So that's set. The other ones we might move around a little bit. So keep an eye out for that, because that will change. We expect it to change. Okay, some practical things. We will leave both the Thursdays, this week and next week, empty, so that people can do outings if they like. And we will come up with a set of possible suggestions, you know, like the Vasa Museum, for example, is the obvious one. I think people should really visit because it is quite unique. and so on. Lars suggested the Stockholm Beer Festival, that apparently is on, but of course he is has special interests, as you might. Right. So that's the plan. There is a reception today at 5 o'clock here. Right?
Yeah, around.
And again, his special interests have seen to it that at least liquid intake could be seen to. I don't know. We have a kind of not a banquet, but a buffet planned for Friday at 7:30. We thought a buffet would be good because again, there's an informal way of talking to each other, etc. And that's in the restaurant here as well, right? Outside the restaurant. Okay, well, we have many of us had lunch. And next Wednesday evening, after the only talk we're planning to have in the afternoon, so for people that are just here, the general interest, there will be a talk on gravitational waves and numerical relativity next Wednesday afternoon by Luciano Rezzola from the Albert Einstein Institute, and that will be at 4 o'clock, I think we decided after some deliberations. And after that, we might have some other social event. We'll just wait a little bit and see how the weather develops and decide that a little bit later. A couple of practical things. The talks will be videoed, right? Because all talks given at this institute, I believe, are videoed. They tend to be put online fairly swiftly. So if you have any objections to being on television or being abused like that, then you should let us know. Otherwise, if you don't, and I really wish, hopefully you don't, if you could give your slides as well, a copy of the slides to Lars, ideally before the talk, so we can speed up this process of making things available online, that would be great. One particular reason for that is that we are currently discussing with the Melbourne group, Andrew Milatus's group, he couldn't come, and he's still interested in taking part in some shape or form, so we're discussing how we could best do that. And it might be that for that it would be very useful if we had the talks online before the talk is actually given, because that way we could just only have to rig up, say, sound, and they could still take part. That's pretty much it, I think. Anything that comes out of the program or the discussions you have here, I'm sure that Axel would be very happy if you acknowledged Nordita's support in papers that come out. Any practical questions about what to do and how Stockholm really works and how Nordita works, please don't ask me, because I have no idea. I've been a foreigner now for almost 20 years, so frankly I don't understand this country anymore. So they go ask, I think, Laila in the first place, because she really knows how this works. Okay. So that's pretty much it. I think I ran over a little bit, sorry about that. It is with great pleasure I'll ask Jim to give the introductory survey of what this, neutron star is all about and what the program is supposed to do.
Okay, thank you, Niels, and thank you for the invitation to speak here. So, I was asked to give an introductory talk both about neutron stars and about some of the topics that will be focused on in more detail at this workshop. So, what I'd like to do then is give a general review of the entire neutron star and its pieces, go into a little bit more detail about what theory can tell us about the extreme properties of neutron stars, some general constraints that we've already been able to achieve by looking at pulsars. If there's time, I actually slipped this to the end. If there's time, then I'll mention a few things that we can learn from neutron star cooling. But for the purposes of this meeting, I think the rest of these things are probably more relevant. So there's an important relationship that exists between the pressure of neutron star matter at densities near the nuclear saturation density and the radii of neutron stars. So one of the important things that observations will hopefully help us learn in the near future will be tight constraints for the radius and therefore for the pressure of matter. And at the same time, there are laboratory experiments and theoretical developments that are bringing us from the other direction to limits on the pressure of matter as well. So hopefully be able to narrow this problem down from both ends. And this problem is related to the nuclear symmetry energy, which is, by definition, the difference in energy between neutron matter and symmetric matter. Part of the problem with neutron stars is that they are almost completely made out of neutrons, and therefore there's a very large extrapolation that must be done between the properties of matter in normal nuclei and the conditions that are found in neutron stars, not only in density but also in symmetry. Several of the problems that we'll be looking on in the next couple of weeks will deal specifically with properties of the crust, and so one important aspect is the location of the core crust boundary, which we'll see has a important dependence on the nuclear symmetry energy that also controls the thickness of the crust and many of the observables that we will find. And then we'll look a little bit at some of the observational constraints for the crust. Okay, so this famous picture was produced by Danny Page, and I guess it has been shown so many times that when Danny uses it, he uses the black and white version. That I think he's the only one that's allowed to use the black and white version. So for us, the important part of this figure is indicated here, defining the 5 important regions, each of which will play a role in different properties of the star. Beginning from the interior, where we know very little. This is from a few times nuclear saturation density to the center, which might be as much as 10 times nuclear saturation density. We really don't know what the composition is. Are there hyperons or Kane condensates or deconfined quark matter or mixed phase between some of these phases and uniform nucleonic matter? The conditions of superfluidity in the interior are rather speculative as well. Closer to nuclear saturation density and ranging down to the density at which nuclei will begin to appear is the outer core, and this is primarily composed of uniform matter of neutrons and protons, perhaps 5 to 10% protons, and the rest neutrons. There's also electrons and muons. And then in the crust begins at about half nuclear saturation density, where the matter will separate into dense clusters of neutrons and protons, nuclei, and a vapor of neutrons that exist outside. And this phase transition is possibly marked by a pasta or Swiss cheese phase, and which nuclei may take on many shapes, ultimately becoming deformed, and then gradually approaching spherical, being spherical in nature as we get to the lower densities. The outer boundary of the crust is usually taken to be around a million, around a few tens of grams per cubic centimeter. At about 4 times 10 to the 11th grams per cubic centimeter, the neutron vapor that exists outside the nuclei will disappear. The envelope and atmosphere of the star are very important for neutron star cooling. The X-rays that are observed and the optical radiation that are observed from neutron stars are controlled by the atmosphere of the star, which is about a centimeter to an inch thick. And the envelope of the star, which is also rather narrow, acts as a thermal blanket on the star and will control the rate at which energy is released. So there can be a considerable difference in observed temperatures depending on what the actual composition of the envelope is. Is it primarily light elements like hydrogen and helium, or is it dominated by iron? So the usual equations of neutron star structure discovered by Tolman, Lattimer, and Volkoff from Einstein's relations are equation for the pressure gradient and the rate at which mass accumulates in the interior. So little m here is the enclosed mass, epsilon is the energy density, P is the pressure. So an equation of state which will control how epsilon depends on P or vice versa, And that, with that information, one can then obtain the mass as a function of central density, and the radius as a function of central density of a neutron star. It's interesting that there are a few analytic solutions of these equations that are applicable to neutron stars. The most famous one is the uniform density result, where the energy density is treated as being independent of the pressure and is a constant in the star. Another interesting one is the Tolman 7 solution, discovered about the same time as these equations were first written down. And that posits that if one assumes that the energy density behaves quadratically, decreasing in the interior, then an analytic solution can be found. And there are several other analytic solutions, but the most important other solution, I think, is Guptal's solution, in which a specific equation of state is proposed, and with this particular relationship, then an analytic solution again follows. And it's interesting to note that at very low pressures, where this term, okay, P star is a parameter, so at very low pressures, this term is negligible compared to the square root term, and this relationship then is that pressure is proportional to energy density squared, so that's the extension of an n equals 1 Newtonian polytrope into relativity. So one can view this then as an extension of a polytropic relation into general relativity, and that's very useful for understanding some properties analytically. So using the TOV equations and a specific equation of state, we can form these different black and green curves depending on that equation of state. So for very low central densities, the radii of neutron stars are very large, the masses are very small. The minimum masses of a cold neutron star tend to be around 1/10 of a solar mass, with radii of about 300 kilometers. However, we don't believe that there's any mechanism of producing neutron stars with masses less than about 1 solar mass. So only the portion of these curves above 1 solar mass are actually interesting from the point of view at this time of observations. One aspect of general relativity that's clearly significant is the fact that for any equation of state, there's always a maximum mass. This doesn't occur in Newtonian gravity. The masses could tend to arbitrarily large values. So these curves are terminated at the maximum mass. Beyond this point, the matter would be unstable and would collapse into a black hole. So each of these black curves represents matter that at low densities is nucleonic in nature, and depending on what happens above nuclear saturation density, if there's softening due to the appearance of a K-anic condensate, as happens in this equation of state, or whether one treats the matter, as in some of these curves, as being due to a non-relativistic potential nuclear force, or in some of these models, a relativistic field theoretical force. There are many equations of state I could have plotted here so that the area would have been black, but I limited it to just a few. The green curves, on the other hand, represent a completely different alternative for neutron stars, in the sense that they would be strange quark matter stars. So if Witten's conjecture is correct, and the ultimate ground state of matter at zero pressure is strange quark matter, and not nucleonic matter, iron, for example, then the equation of state looks more like an incompressible fluid at low densities, so the mass increases with the cube of the radius, and so we get this characteristic kind of trajectory until we get to sufficiently large masses that general relativity becomes important and the curves bend over. You reach a maximum mass as you do for the nucleonic equations of state, and the curves will terminate. So for neutron star masses greater than 1 solar mass, it's possible that the strange quark matter curves and the nucleonic curves could occupy the same region. So measurements of mass and radius alone may not be sufficient to distinguish between these two different possibilities. These regions on this diagram are excluded. The first region because of general relativity. This is the Schwarzschild limit, R has to be greater than 2gm over c squared. This region is excluded by the requirement that the pressure inside the star remain finite, and the green region is excluded if one also supposes that the pressure of matter, that the sound speed of matter remains below the speed of light. And so that gives us a condition approximately that the radius is greater than 2.9 or 3 gm over c squared, 50% larger than the black hole limit. Some neutron stars are observed to be radiating thermal energy, and in a sense they are similar to black bodies. And if one uses Kirchhoff's relations to then infer the radius of the radius of a star from its flux and its temperature, the quantity that's actually measured is R infinity, which is a redshifted radius, and that's because the flux from a neutron star is redshifted from the surface, and the temperature of the star is also redshifted. So the radius you would infer would be similarly redshifted. And so these are curves of constant R infinity. For low masses, of course, R infinity and R are the same, but for any R infinity, there's a maximum mass that's possible, and through the causal intersection with the causal region, which occurs at almost the same place. The maximum in these R infinity curves occurs at 3 gm over c squared, and as a result, that's where those lines intersect. So that's a background for the aspects when we talk about constraints of neutron star radii. We'll be using diagrams like that very frequently. Okay, now we know that the most accurate measurements of masses of neutron stars are obtained from timing pulsars. And so a combination of Kepler's laws and general relativistic constraints can be used to pin down, in some cases, the radii of stars to, the masses of stars to very high accuracy. So this is the case of the recently discovered double pulsar system, 0737-3039. And this figure now is a little over a year old, so I think that the limits are actually even tighter than shown here. Of course, the longer a neutron star is observed and the timing is obtained, the narrower the error bars will go. So the way this curve works is that through Kepler's laws themselves and the fact that the inclination angle, the sign of the inclination angle can have a maximum value of 1, that basically excludes all of the orange regions from this curve, so that the white region is the allowed region for the masses of the two pulsars. So the B pulsar, the lower mass pulsar, is here, the more massive pulsar is, and the more rapidly rotating pulsar is A. These other limits, this is obtained from the fact that the periastron of the orbit, the point of closest approach between the two pulsars, is rotating in the sky. In the case of Mercury orbiting the Sun, that point is precessing by 43 seconds of arc a century, and in this pulsar, it's about 12 degrees a year. And so the limits on omega dot in this diagram show up as a single dashed line, but if we explode the region here, you can see that the limits are a little bit wider. The system is also observed to be to have its period is shrinking. I mean, its period is shrinking due to the emission of gravitational radiation, and the observed rate at which the period is shrinking gives rise to this set of limits here, these triple dot dash curves, which don't show up in the exploded region because that just shows the magnification that I've used for this region. The gravitational time delay and time dilation predicted by Einstein is given by the gamma curve here, and so that's these two dashed lines, which again, only the lower limit, only the lower one shows up in the figure. The upper curve is above this figure. Shapiro time delay is also observed. This was an effect predicted by, or first observed by Irwin Shapiro, that as the pulses travel close to one neutron star, or in the case of the other pulsar, to the other neutron star, the path length of the light gets longer, so one can directly measure then the inclination angle, which is basically what this curve S represents. So that has a finite width to it. So therefore the allowed regions for mass radii are this sort of shaded in region right here. So with the result that to date these pulsars have their masses measured to something like 3 or 4 10,000th of the solar mass, but I suspect that it's even more accurate now. The case of the pulsar 1913 plus 16 also has its mass measured to even higher, perhaps even higher accuracy than this one, although this one is going to pass it very soon. So this is a list then of the measured neutron star masses obtained for the gold and silver and blue regions from timing pulsars. It's also possible to obtain mass limits from pulsars, or from neutron stars that are accreting matter because they're in binary systems and the companion is spilling mass onto them. But those are subject to greater systematic errors, and it's not likely in the near future that these error bars will be significantly decreased. So they're useful to keep in mind, but they're not very good at the present time of actually constraining masses of individual neutron stars or helping us determine what the maximum mass of the neutron star is. The double neutron star binaries, several of them have had their masses measured by observing more than one general relativistic effect in them to pin down the inclination angle quite precisely. And so the 1 sigma error bars are shown here, but in most cases they're very, very small. In other cases, the more measurements are still needed to narrow the inclination angle. In the case of white dwarf companions to pulsars, we have this set of results. Some of the stars have their masses measured quite well. Other ones, the masses are still quite uncertain. It's interesting that there are a couple of ones that Frere et al. In 2007 has discussed where the centroid of the masses are quite large, greater than about 2 solar masses. But until the inclination angle for these systems is more tightly determined, I think we have to take these with a grain of salt. A system with a neutron star, with a main sequence companion, has had 2 different general relativistic effects observed, and the inclination angle is now more tightly constrained, and that has given us a mass of something like 1.67, plus or minus 0.03 or 0.04 solar masses, and so this may then very well replace the Pulse-Taylor pulsar as the lower limit for the maximum mass of the neutron star. So it's going to be 15% larger than this pulsar. So this star has been discussed by Frere et al. In a number of conference proceedings in the last year, but it's not yet published. There are 2 systems in globular clusters, 2 stars in the same globular cluster, the Tarazan 5, and again, the inclination angle is not very well determined in these systems, but if the inclination angle for these 2 pulsars is taken as random in orientation, then to 95% confidence it's claimed that one of these stars has a mass greater than 1.68 solar masses. So there's greater evidence now than there was a few years ago that neutron stars of greater than 1.4, 1.5 solar masses are possible, but the information is coming slowly, and perhaps one of these systems will also push that limit significantly higher. So the maximum mass of the neutron star will certainly play a role in pinning down the equation of state, and we'll see that that's important at looking at the equation of state at very high densities. So now I'd like to move into a discussion of determining the extreme properties of neutron stars theoretically. And Friedman et al. A few years ago suggested that one could obtain the most compact neutron star configurations, in other words, the ones that could rotate most rapidly, and the ones with the smallest radius for a given maximum mass. That would occur when the low density equation of state is relatively soft and the high density equation of state is relatively stiff. And so if you push soft and stiff to the ultimate, for densities below some fiducial density, call it epsilon naught, we simply will posit that the pressure is zero, and above that energy density we take the pressure equal to the difference of the energy density from the fiducial value, and so this gives us a speed of sound exactly equal to the speed of light. Now, with this equation of state, then this fiducial energy density is the only parameter that appears in the TOD equation, and as a result, the integrations of the TOD equation will scale with that energy density. So from those considerations, one can reproduce theoretically a number of constraints on neutron stars that have previously been obtained. For example, the Rhodes and Ruffini limit for the maximum mass of a neutron star, which can be expressed this way. Here, epsilon sub f is that fiducial energy density. Epsilon s puts this energy density in units of the nuclear saturation density, about 3 times 10 to the 14 grams per cubic centimeter, the density we find in nuclei. And with that, the coefficient is about 4.2 solar masses, and the maximum mass will scale with the inverse square root of this fiducial energy density. The radius of the maximum mass configuration, of this extreme maximum mass configuration, is then found to be very close to 3 gm over c squared. And so these results of Rhodes and Ruffini can be obtained. I'm sorry, it wasn't Friedman at all, it was Karanja et al. From their simple ansatz for the equation of state. You can also show from similar considerations that the maximum energy density that can exist in a neutron star of mass m is shown here. So using this relationship for the largest measured mass also then obtains for us an upper limit to the central energy density of any neutron star. And so this is about 10 times, 15 times nuclear saturation density if the largest measured mass is 1 solar mass, and it scales like the inverse square of that. So this limit is potentially interesting in the event that a neutron star greater than 2 or 2.5 solar masses is ever discovered, because then that lowers this central density to interesting values that may or may not compete with the energy density at which deconfined quark matter might occur. And so this relationship itself could rule out the appearance of deconfined quark matter in neutron stars if a large enough neutron star is ever measured. The Karanja et al. Equation of state, maximally compact equation of state, also predicts, therefore, and you can show that since we again only have one equation of state parameter, when you integrate the TOD equations in axial symmetry to find for uniform rotation, you can then determine what the minimum possible rotation rate is for a given mass and radius of the non-rotating object. So if m spherical and r spherical are the mass and radius of a non-rotating star, then this gives the minimum possible rate at which, or the maximum possible rate, minimum possible period at which that star can spin, and it's about 3/4 of a millisecond for 1 solar mass in 10 kilometers. This limit, however, is a little bit too extreme when it's applied to realistic equations of state. The limit is actually something like 30% larger than that. It's close to 1 millisecond for 1 solar mass in 10 kilometers. So if we put those constraints from spinning neutron stars, the most rapidly known pulsar has a frequency of 716 hertz, and so that particular limit, with the empirical relation previously discussed, would give us a mass radius contour shown by the blue curve here between the gray and the green regions. And And so that already tells us that if that neutron star was 1.4 or 1.5 solar masses, that the radius has to be less than about 14 kilometers. A couple of years ago, an X-ray source, J1739, during a burst, was claimed that a rotational frequency of about 1122 hertz was identified. Unfortunately, this measurement has never been reproduced, so whether or not it actually is a rotation rate remains to be seen, but just for the purposes of illustration, if a neutron star could rotate with 1122 hertz, then this curve here would move up to this red dashed line, and you would see that for a 1.4 solar mass star, that the radius would have to be less than about 12 kilometers, and things would be becoming very interesting at that point. Now, the equation of state at densities above nuclear saturation density is considerably uncertain, and so this curve shows the energy per particle as a function of density for a variety of equations of state. At nuclear saturation, this is in units of nuclear saturation density. At the nuclear saturation density, it's known that the second derivative of this curve, the so-called incompressibility, is around 220 MeV to perhaps 5 or so percent accuracy, obtained from measurements of resonances, of dipole resonances in nuclei. But higher derivatives and the extrapolation of this to high-density matter still is in considerable doubt. So one could parameterize equations of state by the third derivative of the energy with respect to the density. Call that the skewness. So as you vary the skewness, you get, of course, this kind of range. But even knowing a third derivative isn't sufficient. You can see that these curves cross, so as you extrapolate far enough away, then no kind of extrapolation from nuclear matter conditions will be satisfactory. The other aspect of this figure that is important is the extrapolation that has to be made to go from symmetric matter, where we have reasonable control at the nuclear saturation density, to pure neutron matter. And this difference in energy is the symmetry energy. It's quite clear that that's a function of density. At very low densities, the difference in energy is very small per particle, and at high densities, the difference tends to be larger. At the nuclear saturation density, this energy is on the order of 15 MeV, although that value is uncertain to a few MeV, and the derivative of the value at this point, as we extrapolate into the higher density regions, is even less well known, and that has great significance. So people have spent a lot of effort trying to constrain the behavior of high-density matter, and one way in which this can be done is by looking at heavy ion flows. And in a 7-year-old paper by Danielovich, Lacey, and Lynch, using a particular set of nuclear models and examining these ion flows, they suggested that the results were consistent with symmetric matter having a pressure from 2 to 5 times, 4.5 times nuclear density, consistent with being somewhere in this hashed region. This calculation has not been repeated, as far as I know, using more general equations of state and different momentum dependencies, for example, different parameterizations to see how robust this particular limit might actually be. And we compare that to several equations of state. One of the most often used equation of state is by Ockmel and Ponder-Pondé. That's this black dashed dotted curve here, and so that actually falls within this region. If you simply take a compression modulus of 210 or of 300 and just extrapolate to high densities, you get these two curves like that. But I'm not reading the paper. It was never clear to me what exactly was done with the skewness for those extrapolations. Now this is for symmetric matter, and of course for neutron star matter, we then have to perform a second extrapolation from the high densities to lower pressures that would be involved with less symmetric matter. So the pressure of matter in neutron stars near the nuclear saturation density is controlled very tightly by the symmetry energy, and not by other aspects of the nuclear, other parameters in the nuclear force, like the skewness or the incompressibility. And that can be demonstrated very easily if we simply take an extrapolation of the energy of matter as a function of density and proton fraction in symmetry, and including the electrons that we need to neutralize the matter. So this term represents the energy of symmetric matter as a function of density, and then by adding this piece to it in this quadratic, with a quadratic term, the energy density of neutron matter then is reproduced. Now there's some question about whether or not this extrapolation is valid all the way, or at intermediate proton fractions, but at least it's written this way, and using the symmetry energy as being the difference between neutron matter and symmetric matter. For nearly pure neutron matter, this relation should be reasonably okay. The pressure is just the derivative of the energy density with respect to density, shown here, and the chemical potential of the electrons is related to their, because they're relativistic and degenerate, it's related to their density and electron or proton fraction by this. And we can also, close to the nuclear saturation density, we just keep the leading order term in a density expansion that involves the compression modulus, the binding energy at nuclear saturation density. In a neutron star, the matter's in Bethe equilibrium. Neutrons and protons and electrons have reached this chemical potential equilibrium, and if this is violated, the neutrons will convert into protons or vice versa until it is satisfied. So the energy is minimized with respect to the number of electrons or protons at a given density. So applying that to these particular relations, one finds what the proton fraction is in matter as a function of density. See, that's very heavily controlled by the symmetry energy. And the pressure of matter in Bethe equilibrium, we substitute this proton fraction into this relationship, you obtain this result. So here we have a term depending on the incompressibility, and a term depending on the derivative of the symmetry energy, and a final term from the electron contribution. This term is very small, however, because the proton fraction turns out to be very, very small, on the order of a few percent at nuclear saturation density. So, and this term vanishes by definition at the nuclear saturation density. So you can see that in Bethe equilibrium, the leading order term near nuclear saturation density simply depends on the derivative of the symmetry energy with respect to density. So if we look at different models of the symmetry energy as a function of density in units of the nuclear saturation density, for densities up to the nuclear saturation density, different models have significant variations, and even greater variations if we extrapolate them to higher densities, and it's even possible that the symmetry energy could turn over and possibly even become negative at sufficiently large density. So this turning over behavior usually occurs in, that occurs often in Skirm forces, which are non-relativistic potential models, and the models in which the symmetry energy behaves linearly with energy density, extrapolating to high densities, is characteristic of relativistic field theoretical models. Now, some control over the behavior of the symmetry energy at lower densities is in principle able to be obtained by studying normal nuclei, in particular looking at masses of nuclei and neutron skin thicknesses of nuclei. However, because the extrapolation in masses of nuclei is not very great, even for the most massive nuclei, there's a significant correlation among parameters of mass formulas that occurs, and so the actual constraints on the symmetry energy are not as great as we would like. And so we need some kind of orthogonal relationship and possibly measurements of neutron skin thicknesses of lead, which are being undertaken. Chuck, you can remind me, is that going on right now, or does that start soon?
So the Jefferson Lab experiment will start in the spring.
Okay, so starting in the spring, there'll be a series of measurements of the neutron skin thickness of lead, and that, I think, will help constrain the behavior of the symmetry energy below nuclear saturation. And so there may be more discussion of that during this week. So instead of looking at the energy per particle as a function of density, we could also look at the pressure of neutron star matter as a function of density. And so I plotted that for a number of different equations of state that have been used in the literature. And if we look at nuclear saturation density, this is a logarithmic plot of the pressure against density. You can see at the nuclear saturation density there's a considerable variation in the predicted pressure of neutron star matter. It's fully a factor of 6. And again, I have to say that these are just equations of state that have been taken from the literature, and many of them are quite old. So one of the aspects of this meeting, I hope, will be to discuss how much we can constrain this particular behavior at these densities.
It's really hard to censor curves once they've gotten into blocks.
Right. Well, okay, but if we have a set of experiments or a set of theoretical calculations that one seriously believes, hopefully we can constrain this to a smaller amount, and I'll discuss that further in a minute. The other aspect of the curve, besides its wide variation at nuclear saturation density, however, is the fact that the curves are mostly consistent with having a slope of 2. So if we employ a simple polytropic equation of state, we find that the exponent for many of these curves most of these curves almost all of these curves is close to 2. And so if we solve the equations of hydrostatic equilibrium in Newtonian gravity, you can easily show for this equation of state that the radius of a star depends on its mass and this particular constant in this way, where the exponent on k is 1 over 3 gamma minus 4, and the exponent on the mass is gamma minus 2 over 3 gamma minus 4. So if we substitute gamma of 2 into this relationship, we find a prediction that the radius of the star will depend on some average pressure in the star to the square root, and depending on what that average density is, which we then scale like the inverse power of that density, and the exponent of the mass will then be 0. So this is a very convenient analytic demonstration of the fact that the mass radius curves for many of the equations of state have a radius independence around 1 or 1.5 solar masses. The curves rise vertically in that figure. So to check this analytic relationship that would obtain in Newtonian gravity, Prakash and I simply tried to explore how the radius might depend on the pressure at a particular density, and we found, in fact, a simple relation that, to a very good accuracy, the radius depends on the pressure rather to the 1/4 power rather than the half power. And furthermore, we were able to show that using Buchdahl's solution, which is the one general relativistic analytic solution that has a definite pressure density equation of state in it, one can show for Buchdahl's equation of state that the predicted relation between radius and pressure at a given density would be very close to the 1/4 power. It ends up being 0.24 instead of 0.25. And to just remind you again that the pressure of matter then, if this fiducial pressure is taken, density is taken to be close to nuclear saturation density, it just depends on the square, on the derivative of the symmetry. So here's the results that I found with Prakash, that if we simply took the product of radius and the inverse 4th power of the pressure for all of those different equations of state and a few others as well, the lower curve, for example, shows what happens if we take configurations that have 1.4 solar masses. And if we look at the pressure at, say, twice nuclear saturation density, and look at, for 1.4 solar masses, these different equations of state have different predicted radii that range from 9 to about 15 kilometers, that this correlation, that r times p to the minus 1/4 is nearly independent of the actual radius of the star. That also holds if you go to 3/2 nuclear saturation density or nuclear saturation density itself, although the correlation becomes a little bit less precise as we go to smaller densities. So the implication is that a measurement, and I should say that several of these equations of state do have significant softening that occurs above nuclear saturation density. So even given that, the predicted radii of stars is a pretty good indicator of what the pressure of matter is in the range of 1 to 2 times nuclear saturation density. So we can use this in either direction. If we measure the radius of the star, we have some prediction for the pressure of matter. And if we have some way of measuring the pressure of matter from laboratory or theoretical means, then we can predict the radii of stars. And I guess it will be a competition to see who finishes first in that. Recently, I've been in touch with Joachim Schwenk about the issue, and he and Kai Hebler are working on a current calculation using chiral effective field theory forces for pure neutron matter coming from Entem and Mockley, and they fit this to neutron-neutron scattering and to low momentum interactions, such they say that there are no free parameters left in this force. And given the observed limits from scattering and low momentum interactions, they've obtained a band of pressures as a function of density that follow this green region. So if you take at nuclear saturation density about here the limits of pressure, this implies a radius of a neutron star. Then if this condition is satisfied by the force, no matter what happens at higher density, the prediction is that the radius of 1.4 solar mass stars will be about 12 kilometers with an error of a little bit more than, if you just propagate errors, 1 sigma error bar is about 1.2 kilometers. So that's a very interesting result. And so the question is, how valid are these upper and lower limits? Can we do better? Is this theoretical calculation good enough that we can trust this result, and so forth? So I hope there will be some discussion of this week or next week. So comparing the Hebler and Schwenk predictions for the behavior of low-density matter, that's this blue region. So now instead of pressure, I've plotted it as a function of energy, or particles as a function of density. Compared it to calculations they did Joachim did with Chris Pethick in 2005, which covers this region here. The Akmal et al. Equation of state, which is believed to be one of the better low-density equations of state, is shown by the green triangles. And you do see, however, when you take the derivative of this curve, that the Akmal et al. Force seems to have a higher pressure than located within this band. So that may indicate that we need to extend that band to somewhat higher pressures than I illustrated, if in fact this is still a believable result. And then there have been a few other calculations of low-density matter that are also indicated in this figure.
The density scale, so it's just all below nuclear matter density.
That's right. It's all below nuclear matter density. But fortunately, even the relationship between radius and pressure nuclear matter density, although the errors are greater than they would be if we could measure the neutron matter at 1.5 or twice nuclear density, it still constrains the radius reasonably well if this band is believable for the energy. I mean, for the pressure. Okay, so there are many kinds of observations we could make to try to constrain the radius of the star, and the ones that the kinds of calculations that refer to the bulk properties of stars or the behavior of matter at densities above nuclear saturation density are contained in the magenta blocks here. So measuring radiation radii from X-ray thermal emission, looking at X-ray bursts from accreting stars, internal properties gleaned from consistency with neutron star cooling measurements. It's possible in the double pulsar system and maybe future compact pulsar binaries that spin-orbit coupling may allow us to measure moments of inertia. That would be a direct measurement of the radius of stars. Neutrinos from protoneutron stars would also help us constrain binding energies, which is also then dependent on the mass and the radius. There have been several attempts to use pulse shape modulation from light bending in GR to constrain the redshifts of neutron star surfaces. And it may be possible to use gravitational radiation from neutron star mergers. This could come either from the final instant of coalescence of the stars, or possible in the earlier, less noisy phase of gravitational wave emission coming from tidal deformations of the neutron star, which again is sensitive to the radius of the star. The observations that hopefully will be discussed more in this workshop are shown in red down below. Glitches could constrain crust properties, cooling timescales from X-ray transients, where the crust of the star is believed to be heated by accreting matter, and then when the accretion stops, we can watch the crust cool off. This gives us some indication of what's going on. Seismology from giant flares and magnetars. I think Anna Watts will be talking a lot about this. Or I guess you're giving a talk about this, right? Yeah. And gravitational radiation from neutron star mountains. Chuck Horowitz has done some nice theoretical calculations on what the maximum size of a mountain can be from molecular dynamical calculations. And some of the quantities we might hope to measure are this. Beta is just going to refer to the compactness of a star in geometrized units. So we've already discussed the radiation radius, and what's actually obtained, however, from a thermal measurement is not the radiation radius even, but rather the apparent R infinity, in other words, the angular size of the star. And so that depends also then on the distance to the star. If we can measure the redshift, that's directly a measure of the compactness. From the fallback of surface layers that have been thrown up in X-ray bursts, it's possible by measuring the maximum fluxes achieved in those explosions that could be a measure of the so-called Eddington flux, which is basically the maximum radiation that could balance gravity in a layer of optical depth kappa. So that depends on the mass. Of course, it's a flux, so it depends on the inverse square of the distance, and it has a general relativistic correction like that. If we can measure the moment of inertia, I said that's a direct measurement of mass and radius. It turns out that for realistic equations of state in which maximum mass is greater than about 1.6 solar masses are predicted, that there's an almost independent of the equation of state. This relation for the moment of inertia of the star depends only on the mass and the radius of the star. Same occurs for the binding energy, and it's only a function of mass and radius to first order. If we have different observations that can determine for us the crust thickness, for example, from seismology or from cooling timescales, then again, we can try to formulate a relationship for the thickness of the crust in terms of the radius of the star. And in fact, for using just the properties of the crust, using the fact that the TOD equations simplify near the surface of the star, we find that in terms of the single parameter of the equation of state, this variable h, which is related to the difference of the neutron chemical potentials at the core crust boundary and at the surface of the star, that in terms of the single parameter, this quantity is then determined as a function of mass and radius. And also for the fraction of the moment of inertia in the crust compared to the entire star, again, we get a relationship that depends on mass and radius and a single parameter of the equation of state having to do with where the core crust boundary is. So, looking at radiation radii, we can measure this particular quantity, the apparent radius of the star. The observational uncertainties include the distance to the star, the amount of absorption, since most of the emission from the star, or a large fraction of the emission from the star in hard ultraviolet and X-rays, will be absorbed. So this has to be a parameter of the fit to the observed spectrum. And then a large uncertainty is due to the unknown atmospheric composition of thermally emitting stars. So the best chances we have for accurate radii measurements are ones in which we can measure the distances to high precision, which might be possible for some of the nearer neutron stars with parallax. And another possibility is to look at quiescent X-ray binaries and globular clusters. So these are very old neutron stars that have recently been heated because of episodes of accretion from their companion stars. The advantages obtained in these systems are if the distance of the globular cluster can be measured to a few percent, that would be very good. It's also suspected that the recent accretion would have submerged or suppressed the magnetic field on the surface of the stars, and the accretion would leave an atmosphere that would be dominated by hydrogen. So this makes it the easiest possible atmosphere to deal with. So an example of a nearby neutron star is one that Fred Walter discovered about 15 years ago. This is the discovery photograph using the Rosette telescope with the stars here. He predicted that it should be, if he extended the blackbody spectrum using the observed temperature, inferred temperature of the star in X-rays into the optical, he predicted that it should be observable with the Space Telescope, and it actually turned out to be something like 5 times brighter than that simple extrapolation. It's also observed to have a bow shock. It's moving in this direction, and the position of the neutron star is at the end of the arrow here, and there's a bow shock oriented in the same direction as its motion. So it's likely that it is a pulsar, that the pulsing radiation is exciting this interstellar medium as it passes through it. But the level of pulsation of the star is only about 3%, so we're outside the name. Sorry about that. So, unfortunately, the atmosphere of the star is not known. A lot of observing time was devoted to the star, but the spectrum of the star was almost completely featureless. As a result, the composition is still very uncertain. Nevertheless, given the measured distance of the star, about 120 parsecs, although recent estimates have raised this by maybe 20%, give a lower limit to R infinity. The best fit to the spectrum is obtained using a heavy element atmosphere. And if you use that, you get an R infinity of about 16.5 or 17 kilometers, which puts us in the larger radius range for most masses. But again, I say it is possible that the distance has been underdetermined, and that would push this limit even farther. If it was assumed to have a magnetic hydrogen atmosphere, basically with a magnetic field large enough to basically suppress the atmosphere with just a very small atmosphere as a result, the atmosphere basically condenses on the surface, that would give a spectrum consistent with R infinity being about 17 kilometers with a distance of about 140 parsecs. So again, we get a measurement something like that. But again, this is pretty uncertain because of the unknown surface composition. So the better possibility in the near future might come from looking at globular cluster sources. So Webb and Barrett put together this compilation using neutron stars observed in 3 different globular clusters, 47 Tucanae, M13, and Omega Centauri. And to 99% confidence, the mass and radius that they obtained by fitting the extinction and the flux and temperatures for these neutron stars lay between these 2 bands. colors being indicative of the particular object. So the upper limit for M13 was this dotted line, the lower limit is in this unexplored region. So they performed a series of calculations for models of different masses and radii within the unshaded region, and then took the models that fit the measurements. That's how they determined these mass and radius contours. What's interesting about this is that although each of the limits itself is very poor, if one assumes that one equation of state has to pass through all of the uncertainty regions, then it implies that the equation of state is something like one of these sets of curves, where it can pass through the Omega Centauri region for low masses, but also reach the 47 Tucanae curves for larger masses. So this is an example of even very poor data. If we have it for enough different sources, by combining that data, we might be able to establish more severe limits on the equation of state than for a single object. So clearly this will be an important thing to explore.
1 sigma or 3 sigma?
This is 99% confidence. So 3 sigma. Another example is cooling following an X-ray burst. This is Ariel Ozell has been pushing this technique quite a bit lately. In an X-ray burst, the surface layer is lifted off. There's a maximum flux observed where the temperature and flux both reach a peak, and the apparent diameter is R infinity over d squared basically reaches a minimum. And then the flux, as the layers fall back to the surface, the flux is observed to decrease, and the apparent size of the emitting region approaches a constant at late times. So in principle, this gives a measurement of the Eddington flux, if that's where the maximum of these curves are, and also a measurement of the apparent size of the star. And since the Eddington flux, if we know what the opacity is then a measurement of mass and radius. And here we have another measurement of mass and radius. And then if the distance is also determined independently, then this will give us contours in the mass radius diagram. So for the star, okay, so for the source EXO 1745, Ozell's published results indicate a 1 sigma error contour, that's this green region, and a 2 sigma error contour, that's this blue region. I've tried to reproduce those calculations with Andrew Steiner using the Monte Carlo technique, in which we use the same errors in flux, distance, and apparent radius that she has used in her paper. She's using some kind of boxcar method to limit her error, to do the error propagation. We're simply using Gaussian error, Gaussian limits for the error. And in fact, we find 1 and 2 sigma error contours that are much, much larger than what she's calculated. She has 3 other sources for which she's got similar measurements of mass and radius, and again, for everyone we've studied, when we use a Gaussian error and standard error propagation, we get much larger error regions than what she's coming to conclude. So perhaps this is something that can be discussed as well. But again, given the fact that several different sources are now observed and more will be found in the future, again, combining even poor results from a single source when we have multiple sources could be very useful. So I'd like to finish then with the discussion that focuses more on the crustal properties of the star. And this will be very brief, since these are the topics that are going to be addressed in more detail later on. So here's a picture by Watanabe and Sonoda, again emphasizing the different layers that we obtain in the crust. The possible pasta phases would occur near the inner crust outer core boundary. And so there, Oyamatsu's interpretation of what the different phases might look like in a simplified sense would be spherical nuclei, where you go to spaghetti phases, and then to plates, and then hollow tubes, and finally to spherical bubbles. This is no doubt an oversimplification, And Chuck may have more to say about this, but if we, oops, I got out of order. Oops. Watanabe's recent calculations indicate that at low densities they get roughly, well, spherical blobs. These are supposed to represent neutrons and protons. And then they get a transition to a tubular rod-like shapes, and then plates, and then some other kind of funny shape here, and finally spherical holes that appear. But I think the results that you're finding, you and your collaborators are finding, are somewhat different than this. So maybe there can be more discussion of the influence of pasta. Another difference is that I should mention, however, that these shapes are calculated for relatively large proton fractions. And in the crust of the star, at these densities, the proton fractions will certainly be less than 10%. And I think through these calculations, the value of 30% was used. So this refers more to supernova-like matter than to neutron star matter. And nobody's done calculations yet for real neutron star matter in terms of the rate proton fraction. So it's an open question as to what kind of pasta, if any, will exist. Now, as to exactly where is the core crust boundary, one measurement of where that is if we simply take uniform matter, push it to lower and lower densities, and simply ask when it doesn't become unstable to small density perturbations, and you find a very simple thermodynamic relation for that. And it turns out that that condition then is very, very sensitive to the symmetry energy. And we parameterize the symmetry energy, for example, by its value at nuclear saturation density and its derivative at nuclear saturation density, which is proportional to this L parameter. Then you find that the density of the transition between uniform matter and nuclei can range from very small derivatives of the symmetry energy from almost at the nuclear saturation density to values considerably less than a half of that. So this is a very oversimplified calculation just using this simple equation of state that parameterizes the symmetry energy only in terms of its value at saturation density and its first derivative. So that's certainly oversimplified, but it does indicate the general trends of how, as you increase the density dependence of the symmetry energy, you push the core crust transition to lower and lower densities, and the crust will become thinner and thinner. And just to repeat, if we parameterize the position, this quantity h by the difference of chemical potentials at the core crust boundary and the surface in units of the rest mass, you can find, using the T of V equation as it applies here to the surface of the star, you get a simple relationship that involves only the radius, the mass, and the position, and the radius of the star where the core crust transition is, which is separate, different from r by this quantity delta. So you get a very simple relationship between the crust thickness and the mass radius and this one parameter of the equation of state. The crust cooling time scale, similarly, that'll be proportional to the specific heat divided by the opacity times the crust thickness squared modified by this general relativistic factor. So again, that can be related to the mass radius and this h factor that depends on the core crust transition. And the fraction of the crust the fraction of the moment of inertia that's in the crust can again be expressed simply for different equations of state, simply in terms of this one parameter of the equation of state and the mass and the radius. So pulsar glitches are observed in many pulsars. The Vela pulsar has the largest number of glitches observed so far, and if one looks at the total amount of angular momentum apparently transferred from one region of the star to another, causing the glitches, and although the glitches occur at rather irregular timescales, the amount of angular momentum transferred nicely averages over time. You get a nice straight line behavior here. And simply following through on this, then you can then determine the fraction of moment of inertia that's in the crust of the star compared to the moment of inertia that's in the entire star, and you get a estimate that it's a little bit over 1% in the Vela pulsar. So the model here is independent of where the superfluid that might be spinning more rapidly than the rest of the star, and that causes the glitches. But the word crust here basically limits it then to the outer part of the star. But maybe Bennett will have more to say about how this might be applicable to other kinds of theories of where the glitches originate. If we assume that it's just in the crust of the star, then that limit, and using the smallest possible value for the pressure at the core crust transition, we get a minimum estimate for what the radius of the star is for a given mass. It's given by this curve, as we go away from the minimum possible transition pressure to larger transition pressures, we would move it into this particular range here. So glitches observed in Vela basically rule out these regions of mass and radius for the Vela pulsar if this model is believable. It's also possible to observe the heating of neutron star crusts that come from accretion, and so this is taken from a recent paper by Yakovlev, and basically it shows the luminosity observed as a function of the accretion rate, and the implication is that for this particular star, that the star is cooling so rapidly that it's basically explainable only by the direct Erker process involving nucleons. That the standard non-exotic or non-direct Erker process cooling mechanisms basically predict much too large. Would predict much too large a present luminosity than is now observed from the star. So there's some indication that maybe rapid cooling is occurring in these stars, is obtained from those aspects of the crust. And so the last thing that I'll mention that Anna is going to talk about in more detail is by looking at magnetars, perhaps we can be observing surface modes of vibration, which would be more likely to be these kind of torsional modes rather than radial modes. And a very naive interpretation of SGR 1806 and the modes observed here, perhaps the fundamental mode at around 30 hertz and an overtone mode at 626 hertz. If you simply analyze those two particular modes together with uncertainties in the relationships for the crustal thickness of the star and uncertainties for the shear velocities in the crust, it's possible to estimate these bands of uncertainty in mass and radius that come about. So if it's possible to actually determine which modes are operating in a particular magnetar flare, then perhaps several of these overlapping curves will result in that could be a useful constraint on mass and radius as well. Okay, so that's basically where I wanted to conclude, and that's covered some of the topics that will be addressed in the workshop, but not all of them, and so I hope that that's been useful.
Thank you, Jim. I think we should take some questions. People have any after that?
Okay. You mentioned the you used the book of equations for the same. I just mentioned that generalization, exact solution, with actually two parameters.
For the equation of state?
Yeah. Well, I happened to find it several years ago.
Oh, really?
Yeah.
Oh, I'd be very interested in it.
Yeah, okay.
Of course.
I can give you
It's not generally known then, I guess.
well, maybe not in this community.
At least to me, yeah. Okay, so that would be very easy.
Yeah, because I mean you can basically model both the low density and high density in chemistry. It's still quadratic in the model.
For an outsider, I mean, it's a bit hindering number of equational states from your blocks. And
Yes.
then
Oh, that was just a minimal estimate of it.
So let me ask a question about just the simplest parameter that you, this 220 MEV value for the compressibility, you said that's now tied down to a couple of percent?
Perhaps 5, maybe 10%, yes.
Because you also quoted a paper which I think had 2 lines, one for 220 and one for 300. Whether you agree that it's
Just because
otherwise it wouldn't make any
just
sense.
because the experimentalists claim it's pinned down doesn't prevent people from using equations of state that have much wider range just to see what happens. And so a lot of people are using compressibilities of 300 as not so much because of the behavior at nuclear density, but because of what it predicts at higher densities.
So
it's used as the compressibility is often used as an ansatz to give you different high density behaviors. Okay, but technically, that value at nuclear saturation density is understood quite well. But because equations of state are usually very simple and don't have that many parameters, you still need some freedom to. If you want a large range of what happens at very high densities, you have to adjust some of the parameters that might otherwise be well fit. So people do that instead of just introducing more parameters where they could, fine tune it around nuclear density and then still give them a wider range of high densities. It's just people's laziness, I think, is why you see compressibilities of 300 being used. Because I think we should be using at least where we can constrain things, we should be using those values.
There's actually, I think, a new constraint. I don't know how useful it is, but in a proton-neutron superfluid system, you've got 2 sound modes. And so if you apply the kind of standard causality argument, it gives you another constraint, and that's directly on what you would call the symmetry energy.
And so this is at densities.
Well, it's a general argument.
But for which densities would this be?
For arbitrary kind of equation of state.
It must break down at a sufficiently high density.
No, there's no.
Okay.
It's a model independent, like what Ruffini would have argued.
Just out of curiosity, is there a reference for that?
Yeah.
Look at?
Lars Samuelson, General Relativity and Gravitation article.
All right.
Okay, that could potentially be quite useful.
Well, we could discuss that in more detail because that's very recent. Okay, anyone else? All right, well, let's thank Jim again. And so let me suggest that for those hardcore people that are taking part in the program, when we meet again at 4 o'clock to have a little discussion about what we're going to start talking about immediately, i.e. tomorrow. And have a little, otherwise, we'll leave the planning for tomorrow and after tomorrow, which is a really bad idea. So grab a coffee and refresh yourself.
Please grab the reception. That's fine. Everyone. People will solve it very easy. This building, if you go for a cup of coffee, then there's beers there.
That's right. Would you be working in a different building?
Yeah, so I have created some programs.
I give you my card.
Somebody look.